we are moving on from design space for XR to beyond Earth. XR exploration for space architecture and robotics is the next topic. And I was very happy to see you, Valentina, at Space Kai this year. I have been there too. It was an awesome conference here in Cologne at ESA. Really, really great conference. And now she's here. She flew in this morning. So you are the one with the farthest way here. There's somebody else from Heidelberg, to be honest, also back there. Also awesome. She's from Italy, so she won. Yeah, she is Dr. Valentina Sumini, space architect and engineer, habitat design, in situ construction methods, and soft robotics. She is at the Politecnico di Torino and MIT lab at the MIT Space Exploration Initiative. And Valentina will look up into the orbit while she focuses in her talk on the upcoming ESA lunar mission with concrete insights into building construction and habitat design for extreme environments. Please welcome her with a warm round of applause, Valentina Sumini.
Thank you so much. I'm very honored to be here with you today, and I hope that you enjoyed this presentation. I believe it's a little bit far from what we have seen before, but indeed there are some interconnection because the technologies somehow are similar, but just used in different contexts. Just a brief overview of my activities, since I think that not many of you knows me, but as has been kindly said before, I've been working in 3 different environments. One is, of course, Politecnico di Milano and Torino now, where I'm teaching. I'm visiting professor in the space architecture domain. So I teach students how to design for the Moon, Mars, for LEO, for inhabiting other celestial bodies. And then I'm also a researcher in the space architecture domain at MIT Media Lab within MIT Space Exploration Initiative. That is a very cross-disciplinary environment where you can really design for space at different scale. And in fact, I've been the opportunity to do prototype testing within parabolic flight, launches on the International Space Station. We do also develop algorithms to enable and democratize the design for space projects to several students and researchers. And we also collaborate with space agencies like NASA and ESA. Also, doing engineering research within Ecoisia, that is a company that actually is dealt in automation and robotics, and this is where also robotics plays a key role in my research. So far, what are our goal somehow is just envisioning the next generation of humans that will live on other planetary bodies. So we're going to become a multiplanetary society, and this, of course, it's a vision. It's an artistic vision how we look like, for instance, inhabiting in lunar orbit or in the future in one of the commercial space stations that are currently built in the coming days and years. And so far, what we do is actually do project that we can prototype and test in a relevant environment. So we tested within analog facilities here on Earth. We tested on parabolic flight where we can simulate different reduced gravity conditions. We send projects also on suborbital flights. And so the package of some of these projects have been published in this book, into the Anthropocosmos. And if you want to have a look at that, I think you will see an overview of how it's the variety of ideas and concepts we come up with. But now we are living in a very exciting time. We are living in an era where we want to go back to the moon this time for saying, and this is also part of several governmental space agencies across the globe. Mainly we are focusing on the NASA Artemis because see Europe active also in that domain with the goal of landing women and men on the moon and then enabling them to living there again somehow for maybe more than a few days, but who knows, maybe for months and years. And in that domain now this has come the relevance of space architecture architecture, meaning the fact that we have to design in an environment that we don't know, so we are designing for the unknown, and so we have to be aware of the environment, of course, collecting all the information that we get from scientific data and all the, of course, the information related to space science. And then, of course, we have to include all these thoughts within the engineering and different branches of engineering, again, from structural engineering to mechanics, from aerospace to robotics and computer science. All of these need to be included within that domain. Again, industrial design, because at the core of our exploration is a human. And the man, women are not designed to live in an environment that is different from Earth. We're not designed to live on other planetary bodies. Our body is really not designed for that. And so we have to somehow consider a human-centric design approach. And this is why industrial design ergonomics plays a key role to protect and enable astronauts to perform at their best during that type of missions. Medicine also is a very fundamental piece to take into account, and psychology, because we are designing in an environment that we call IC, that stands for isolated, confined, and extreme. And this means that puts lots of stressor on humans, both like physically and psychologically. And so we have to design for it. And of course, art, because plays a key role in that domain, also for expressing and also for as a way to mitigate this stressor. And so all of these needed to be taken into account when designing for space. So this is actually the pillars of the space architecture domain, and we have to use is a holistic design approach. Over the years, I had the opportunity to develop several concepts. For today, I just listed a few of them. One of these, for instance, is the collaboration with the European Space Agency in designing a moon village. This project dates back a few years ago, and the idea was generating a linear city on the rim of the Shackleton crater at the south pole of the moon. That is one of the locations that Artemis identified as very strategic in the next decades. And within this collaboration that we had, of course, with an architectural firm, Skidmore, Owings and Merrill, that I believe you all know for designing highest skyscrapers in the world. And of course, MIT, as I mentioned before, the research group I'm part of, we had a few astronauts on board, and of course, ESA with all the expertise. And the idea that we had at the beginning was just generating a concept of a linear city on the crater rim, being inspired by Renaissance model, right? An ideal city made of same modules, so interoperability, modularity, simplicity are all taken into account in this concept. So it's a very simple idea somehow. We just have one module and then you populate with the same concept a series of functions and information that are like all embedded for designing this moon village, including also the part of how we can produce energy, how we can sinter the road using local material like regolith, how we can protect our habitats somehow from radiation and micrometeoroid impact. And so how we're going to use local material, one of the key elements of this idea of space architecture is a sustainability. So we are always designing with a sustainability by design approach, meaning that we have to use the minimum resources as possible, and the resources we're going to use are resources that we can find over there, so that we don't have to bring everything from Earth to be really sustainable. And so the idea is just extracting ice, for instance, and the regolith from the lunar environment, using these materials as construction material, using robots, autonomous robots that can create the shielding before human arrival. And what is of interest in here is that this concept back then got a lot of attention, especially within the Biennale Architettura in 2021, where the main research question in the Biennale Architettura in Venice was how we will live together. And there was a moment that in this exhibition just after COVID, So after a pandemic, and there was this very important question, so how we can learn from space to live better here on Earth. And this is the reason why we exhibited this concept, thinking like designing for the moon, inhabiting moon is a test bed of how we can redesign a sort of humanity also, and population, how to live better here on Earth. But of course, as all these great plans then change over time. As I mentioned, this was a project that was developed in 2021, was finalized in that year. But then what happened? Different actors, governments, technology changes, and so what we see now is entropy. And we need to use our intelligence to handle this type of entropy, because we have now several concepts with the technical differences in terms of module design, different strategic exploration goals, and different timing, because different government and different private actors now involved into space exploration don't want to explore at the same time in the same places. And so there's a lot of entropy in that. And so how we can deal with this entropy? And so we started doing this type of research, thinking, okay, maybe a plan where all the city with all the Renaissance model was not anymore the case. But what if we create a system where we don't know yet, of course, the modules, we don't give a predefined shape to all of these, but what we design is a system. Indeed, we start designing based on the algorithm-based approach. So we design a multi-objective optimization system that allows to identify several topology of the terrain and then find the best one given certain aspect of the, of course, the terrain, and then based on the habitability scenario that we have, meaning the very first thing we design for a space architecture project is the mission. For how long, for how many astronauts, and where. Based on these three parameters, you can identify an habitability scenario. How big needs to be the habitat, how you're gonna fulfill this habitat with facilities, like do you need a greenhouse, you need to produce locally, or you can bring food from Earth. So these are all research questions that stems from the main research that is the mission design. And so the mission design parameters we set at the beginning, then the algorithm does the rest, and start designing an infrastructure that using the terrain to locate some inflatable module that are pressurized locally in situ, and then use the material from the extraction to create a shielding against radiation and micrometers, using robotics, using 3D printers, and adapting the toolpath of the robot based on the geometry of the terrain and the pieces that it has to play. And then using mobile robots, you can assemble that. This is one piece of information of this entropy. Then we designed a mobile unit that was able to navigate on the lunar context, is able to adapt, and to have 8 hours of exploration. And so we did somehow several testing scenario about the places it could be strategic to explore based on the slope. And then we define a minimum system that could be enough for 8 hours of exploration, but then could be extended over time and creating a sort of train. So if you attach several modules together, then you create a full habitat scenario, not just an exploration module. And then the interiors need to be, of course, carefully validated in order to create somehow this adaptability scenario with different functions over time. And then another aspect that came into place, so we're used here on Earth mainly, and also in general as a way of thinking to design and build our structure here on Earth, even this beautiful castle, but it's actually built from extraction, from artificially producing material, bricks, masonry, concrete. And, but all of this actually requires an artificial process somehow. So what we were investigating recently in the last years were what if an habitat could grow so that I can send, I can ship to the Moon and Mars the bare minimum material that I need. Imagine like an inflatable membrane that can hold the pressurization, and then nature does the rest, meaning they can grow and then create some sort of shielding, thermal shielding, can create a radioprotective layer. And so this is how we started designing designing this logic, again, through a computational design approach, designing mainly algorithm. This is one, for instance, is based on the similarity of a sea urchin, because sea urchin in the sea are using the shell to protect themselves, and with the same analogy, we try to replicate the logic on a sea urchin, but on the moon. This is why moon urchin in its name. And what we did in this computational design approach is applying a radio protection by design system. This means applying Monte Carlo simulation analysis while we do the topology optimization of the structure, and then considering different materials for this radio protection. Meaning, okay, maybe combining a layer of lunar or Martian regolith. This could be, of course, a thing to give a structural integrity from micrometeoroid protection, but at the same time also thinking to use some biomaterial that could grow over there, thinking of mycelium, in this case thinking of microalgae. Microalgae are very powerful since they are, again, a superfood, they have very good nutrients, and somehow it's also good in the life support system because they eat CO2 and then they create oxygen, and so they're very good in the life support system of the habitat. Plus, they can also have a very inactive way to protect against radiation. And so this is, for instance, a simulation in terms of protons and neutrons of the habitat that you just saw in its different configuration of topology optimization based on the material that I mentioned before. That is lunar regolith and microalgae bioreactors. In this way, you can have a multi-objective optimization in which you design somehow the structure based on different parameters, and you select the solution that the best suits your idea. So again, it's not anymore given a predetermined shape, but you derive the shape from the process, and the process is derived from, of course, the criteria of the Alara principle, that we're going to minimize the risk of radiation exposure to astronauts as low as is reasonably achievable. In terms of growing, we also think about, okay, what the other things that we have to grow over there. One thing is, of course, food. Astronauts can't survive, for instance, on Mars without food. Of course, neither on the moon, but maybe on the moon it's easier to send refreshment from Earth, as it's happening right now at the International Space Station, for instance. And the idea that we had, like for Mars in this NASA project, was how we're going to create an hydroponic greenhouse system that using water as a main system, as a medium to grow crops in order to have a Mediterranean diet for the astronauts. And this was indeed a very interesting challenge, and then there were lots of logic about the importance also of being in contact with nature during, for instance, a long trip to Mars that lasts at least 2 years on the red planet. Somehow it means that you will really miss breathing air and then having a walk in the nature or in a park. And so this is why we try to incorporate the design scenario of a greenhouse also into a habitat design. And based on that, then we had another research question. So with all this food that is produced by a greenhouse, how are we going to optimize the diets, the astronauts' diets with the food that is available in the greenhouse? And so this is why we designed an engineered space kitchen. This is a collaboration between, for instance, Coisia and Rana. I don't know if you're familiar with this Italian brand that makes ravioli around the globe, but it's kind of renowned. And with this project, we identified somehow a way to put in an entire system the greenhouse, astronauts, and an engineered way to process this food. And what we did is, instead of proving that the design was good or bad through a physical prototype, for this type of project, what we did is a VR experience. A VR experience in which we incorporated all the functionality of this kitchen, including all the kitchen tools that we patented because they were like brand new when we designed that. And so for example, you see a pasta towers, a multi-use system for processing food, and some dispensers that are like taking information about the exact nutrients that astronauts require. And what is of interest in here, that in this VR app that we designed, we also try to incorporate a gamification experience. So we wanted to test astronauts and users and chefs because also thanks to this collaboration with Rana, we also had the possibility to collaborate with real chefs about the usability of this kitchen. And it was a really interesting experience because they had the possibility to really test. Now you will see a mock-up of this gamification experience. So the very first part is where you understand how to use all these kitchen tools. And then you are trained how to use it. And then somehow this AR visualization will help every astronaut to become a space chef. And so this is the video, but then now, just in a few seconds, you will see how this gamification experience works. And so you will enter within the app, and you will start saying, okay, the type of astronauts you are, and what are your nutritional requirements. And then based on that, it suggests you some recipe that you can prepare based on the availability that you have on the greenhouse. And then you play start, and what you can see, you get instruction at the top bar of what you have to do to complete your recipe, and you are somehow trained step by step on how you can prepare, for instance, this space ravioli. And this is interesting because also this was good to understand also the speciality of this environment, because, for instance, the reason why we place also a multitude of these kitchen tools is for redundancy. So what happens if you're on Mars and one passed hours breaks? Then this is the reason why you need to place two, right? And so some of this logic also came into play where we started doing this type of design. And what is of interest in this gamification, it is very much rewarding on the user that are actually using it. And so even the training and the feedback that we collect was very much of interest. And then we were lucky enough, thanks also to Tommy Nilsson from ESA XR Lab, to be able to test this kitchen also with the astronaut Matthias Maurer. And we tested several things. So we put in extended reality this concept, and since the entire design was computationally designed, we were able to allow the astronauts to adjust the position and the location, of course, of these kitchen tools and the kitchen elements in his preferred way. So now we have a design branded Matthias Maurer that is actually a good feedback in order to collect. And then we also try to insert a robotic arm inside the kitchen to allow remote teleoperation for the kitchen, for the recipe preparation, if you don't want an astronaut to be there to prepare it. And this is based on a research that I'm currently doing in teleoperating robot from another location, thanks to the fact that they already have a digital twin of the robotic arm in real time. So I can change a place on the tool path of the robot, even outside the robot area, and the robot can recalculate and optimize its tool path in order to achieve that goal. Then last chapter of this presentation is a new way of thinking about this entropy and this intelligence. That is about the Argonaut lander. That is a project that is currently developing, and it's in the framework of Explore 2040. And the idea that this lander could actually be create a new urban logistics, meaning that we go towards an adaptive ecology, because thanks to this lander capability, and of course, as its payload right now is just 2 tons, but then it could be improved in the future, the idea is that we can eventually bring several pieces of our architecture somehow, and then populate an adaptive ecology of modules in the future. This was a successful collaboration that we had with ESA, again with Tommy Nilsson that is here, and MIT Media Lab, my students from Politecnico di Milano. And was interesting because we started rethinking a way in which we could transform a cargo unit here that is actually designed maybe just for cargo mission into a lander that could actually host also a habitat on top. Given the limit that we had of 2 tons, we had to use inflatable structures in order to achieve the goal of having a self-standing structure that could hold pressurization. And then the idea is just having a 2 floors habitat in order to get enough habitable space for the astronauts. The mission is about 4 weeks for 2 astronauts. And then having the mycelium growing in the interlayer of this inflatable shell to create the thermal insulation and also the radio protection layer. And the idea here is to locate all the functions within a logic. So from the airlock, design interiors, then you move through the towards lab to the medical lab, up to the other floor where you have the crew quarters and the social recreational area, including an hammock to look at the stars from the Oculus. And we carefully designed all the materials, the lighting in order to replicate the circadian rhythm, and of course the habitability scenario in these for these two astronauts for 4 weeks of isolation in there, and replicating also the scenario of the circadian rhythm, because if you are on the moon, you have 15 days of darkness and 15 days of light. It is very inconvenient for us as humans. We're not used to that, right? And so playing the lighting, having a key role in terms of the design. And after this presentation, you will also have the possibility to try the XR app that we actually did with the idea of living inside that habitat unit on top of the Argonaut. And the idea of this installation that we currently exhibit at Biennale Architettura in Venice this year is actually make, thanks to this app, somehow everyone a designer and an astronaut. Thanks to this type of simulation, you can really engage with the design scenario. This was very useful, for instance, for the students involved. Usually also in my class, when I teach the students, we always use computational design tools, like for instance, I'm familiar with Grasshopper, and then through that extend it directly to an XR environment to allow them to live and be able to adapt the design according to habitability scenario. And what is of interest in this experience that you will after have the possibility to try is like you have simulated the lighting condition, you have simulated the materiality of the experience, and also the sound that was actually generated by Professor Paradiso from MIT Media Lab, just on purpose for this VR exploration. And also, I think it's important to see the color that now it looks so bright, but when you are inside the VR, of course, the experience looks more realistic and slightly better. But I think this quite gives the impression like how it's important also to use the color to avoid a depressive mood state that you can get in isolation and confinement for long term. And so we had to use the same complementary colors that we have in nature, but in different gradients to make the space more alive, more playful, to allow astronauts to feel less lonely while they are on the surface on the moon. And then last but not least, a very important part of this architecture is the possibility to look at Earth from the habitat. So in fact, we placed a window looking at Earth directly from the lunar surface within the habitat. You see the window there that is actually usually closed through a shutter system to avoid issue with micrometeoroids and radiation, but you can open it up if you want to look at Earth. And then an oculus at the top of the habitat unit that will allow you to see the stars and an hammock that will help you to have these beautiful views. And so this is a preview of what you will all have the possibility to try after this presentation. This is just a few pictures of the installation in Biennale, and the event just happened, I think, a week ago, maybe 2 weeks ago, in Biennale in Venice. Very first picture is with the team, with my students, and then this beautiful event is Sustainable Lightness of Space that we hosted, and then the VR that was not just for adults, but also very playful for kids. And this is a picture that we took just a few days ago. And then, just to conclude, that space architecture is not just about designing a space, a module, but it's about relationship between human and machine, because the interaction, as you saw, is very important between design and life, and between Earth and elsewhere. And now, this is just a quote from Carl Sagan to conclude that we are explorers, and we have waited just too much before going to space again. Thank you.
Thank you very much, Valentina. I knew space travel is fun, but I didn't imagine it that colorful. I wish my home would be that colorful as what you designed for the astronauts on the moon. And yeah, I'm pretty sure the last module will be named as Space Peanut, because it has a little bit the shape of a peanut, which is really nice and cute. Thank you very much for this great presentation, and that was very inspiring. And now we have time for more questions. Do you have any questions for Valentina? From the architect? Let's see, I will hold the microphone for you.
Thank you very much for this super presentation and all these science fiction pictures and virtual realities. It reminds me a little bit of the history of architecture, Le Corbusier, Modular, and Leonardo da Vinci, Homo Circulum. It's very humanistic, it's very human-oriented. But there I have a little doubt. So my question is simply, do you really think that we need human being on Moon and Mars? Because the challenge is very high to bring human being there and giving them a living space and all these psychological, social issues. It makes the development, technological development very, very high. And on the other side, it's my question to you, I could guess that this will do robots for the future, or for a long period. And they will develop, maybe they will do some geodesign, and they change Moon and they change Mars, so that people who come there later could even live there. Or in the meantime, there are only very few people, and the robots do the job, and we do it with virtual reality from Earth. So this is my question. So the fundamental use case, this is my question.
Yeah, so the question is, it's beautiful, but why?
Yes, I think this was a beautiful question, actually, and to answer you properly is just about the timing. So that, of course, robots will go first, and as I mentioned before, we go first to design and create infrastructure that will be needed to protect human life over there, because we are not meant to live on those planetary bodies. And of course, the idea of having robots going there to explore, to build, to design, and having also AI included into that system in order to be as much as autonomous as they can, those robots, I think, is a very fundamental part of this. And of course, humans will arrive and we stand for a long time, and when I say long time, maybe for months or years, only after we reach this level of protection from radiation. So we are totally exposed from galactic cosmic radiation and solar flares. So it's, after LEO, we are in deep space. And so our human body can't, of course, survive on that condition if we don't have enough shielding. And the shielding material and the best shielding material, the best technology to produce the shielding is not there yet. So it's under study. So you're totally right in saying it's not in the super near term, those type of vision for long-term habitability. But it's true that we're going to stay there for 2 weeks on the cislunar orbit, thanks to the lunar gateway that is currently under construction at Alessandria Space in Italy. And it's also true that from that capability of 2 weeks of mission, we could also land, some thanks to the Argonaut, also land people on the moon for staying for a few weeks. Like in this case, it's just 4 weeks of mission. And 4 weeks of mission is totally feasible in terms of radiation protection. So what we do is limiting their exposure, limiting the mission duration. This is what is currently doing, because the technology to have a medium to long-term inhabitation there is not there yet, or it requires a lot of robotic construction before. And so this is the reason why we design a two-level of two time frame, if you want to think of that. Like the Moon Village is a long-term approach. It's more like a vision. Was designed thinking of 2030, 2035, and probably maybe will not even be enough that the time span. But the Argonaut is happening the real near term, and the Lunar Gateway is already under construction. So it really depends on the mission duration and what is the goal of exploration. But I truly believe that human will go back to space and then we will live there in the future, of course.
Thank you very much. And here's the next question from Sebastian.
Obviously from me. As a designated Gen Z, what would be my work times and how would my work-life balance look like? And what have you planned for my personal pleasure and entertainment?
Of course, I mean, like now astronauts work mainly for, I mean, you consider that the schedule of an astronaut is very peculiar because they have their entire day is scheduled in every 15 minutes blocks. And somehow they work for, 8 hours of work minimum, and then the rest is exercising because the reduced gravity pose limits on your body. So you have to exercise quite a lot in order to keep your muscles and your healthy body alive when you are in deep space. So somehow you have to think that you have 8 hours of work, then 2 hours of exercising, and then the rest you can think of between sleeping, eating, and taking care of your free time and yourself. So what is of interest, what you do in your free time, right? So some of them, it's very interesting because I did, for this year, was writing this column in an architectural journal, Domus, about space architecture, and I had the pleasure to interview lots of astronauts for that column. And they all say that what they do in their free time on the International Space Station and is looking at outside the space station, so looking at Earth from the ISS. And thanks to the cupola module, that is like a window, is a 7-window composed, a structure made of aluminum blocks, and then with the glasses inside, that you can see Earth from there. And what is very fascinating from them, that they spend a lot of time in the cupola taking picture of Earth and just observing our planet from there. So this is a very interesting aspect. So this is the reason why in our design we always place a window element. It could be an actual window or even an artificial window. So for instance, in terms of artificial window, you can use projection. We just tested a project that we did that is a Tidmarsh Living Observatory portal. So what we did is putting a network of sensors in a marshland in Massachusetts near Boston, Tidmarsh Living Observatory, and then we monitor, for instance, with several cameras what is happening inside the marshland. We record the sound and data from the environment, and then we replicated a digital twin of that marshland, and we project the information of the marshland in a dynamic way into an environment. We designed a cocoon, and we project on that. It's a multisensory experience, and so for instance, we have also the sound, not just the visual aspect, and also the smell of a marshland. And what is of interest that we tested, thanks to my PhD student, Marta, she went in an isolation for 2 weeks in the Lunares Analog Center in Poland, and they tested, for instance, how important it is to have this type of artificial, because there were no windows. It's like a bunker, so there's no window, no way to see outside. And so she put a projector and she kind of replicated this multisensory experience inside the habitat. And she said she was really relieving having a sort of window, even if it was not physical, but having the possibility to look at outside, because what we give for granted, like breathing air, having a walk outside, is something that you will not lack over there. And so the recreational part, as far as much as I understood, with this importance, like recreating this privileged connection that we have with nature, even other planetary bodies, and having the possibility to look at outside in many different ways and look at feeling the visual connection with our planet.
Sounds a little bit like the holodeck, of course. And imagine you could look at something which is more beautiful than TikTok. They just look out the window and see the Earth and cannot stop looking at that. So I find this very beautiful, to be honest. And it's encouraging that the astronauts just look out of the window. And maybe that's also an answer to the architect's question. Why do they go up there? I mean, if they only just look out the window, I think that's everything we need. That's the why, right? And just write a poem or a song about it, and then it's enough. More questions here, over there.
Anatoly.
It's fine.
Hi. Thank you for this amazing presentation. It was a good journey for us to the moon. I have a question about the training in VR. So you said that trainees, they provided a good feedback. But what about your evaluation of results? Do you see the big difference between regular trainings and VR, and what are they?
Yes, this is a very interesting question. So we have to learn how to use those feedbacks, because somehow, so it's very difficult because if you get, for instance, if you make this gamification and you make it apply to space experts, astronaut, architect, designer, my students, architecture students, that we all give different feedbacks somehow, because there are some bias related to our background, our somehow willingness to find something in a certain place, so our habits, the way we used to do things. And so the very difficult thing is try to do this testing in a place that is outside your comfort zone. This is the reason why, again, I put back my PhD student who did this analog isolation mission. It was very much more interesting to get the output where these space experts were in isolation, simulating the real confined environments, because it was much more realistic, their feedback in that condition, than if you go in a classroom and you place this headset to hundreds of students and then collecting some feedbacks. The reason why is after a few days, a few weeks of isolation, you kind of reframe the way you think of things. You change your habits somehow. You change the way you do things, because you are like obliged to do things differently. And so this is how astronauts actually do. They do things in a different way in space than we are on Earth. And in fact, another interesting feedback is like they don't want to get in a situation of comfort somehow, because they are explorers. They are meant to be there to explore, and they are putting, their lives at risk somehow to this exploration. And so this exploration nature in their activity actually brings a different step of interpretation of the result. And so to answer your question, it really depends on how you do the testing. Because based on how you do the testing, you get the feedbacks, and then you have to interpret the feedbacks in different ways. And so some of them are more reliable because the context is very similar to the actual case study. Other ones are out of context somehow. They can be useful anyway, and then you find somehow if you collect all the data, you will find in a Gaussian curve some of the things that maybe continues to be like good feedbacks, and so you can think, okay, those could be a good starting point, but then it's important also the way you do the testing in that case, because it's so peculiar, the scenario, that is, you have to simulate it. This is the reason why we bring, for instance, VR on parabolic flights. This is the reason why we do analog mission, and we do all these things.
Thank you very much. And I would say one last question, although time is running, but you're already here, right? So we take all the questions. So one question from you.
Thank you very much for your presentation. It happened to be that I was in this class at Politecnico having a similar project as you just presented. And so I'm wondering, as you showed the anemonic structures, like natured, simulated cones, I think it was anemones, right?
Sea urchins, but yeah.
Yeah, so I understand where you come from. I'm wondering, seeing also this rendering, how close is your research to the fact that we can actually build structures from kind of like the material which we encounter on the moon or on Mars? Because seeing all those finishes and all the design, I like, but I feel like this is so far from reality to actually produce it on site. And you also talked about sustainability, and so I just wonder how the ideas which come from the structures of the nature-based structure, which does make sense, to this very far rendering in the end. I just wanted to understand how close is the research already to working together with the experience of ESA and NASA in the end. Does that make sense?
Yeah, so those are two, I think there are two different levels. So the structure, the materiality, and the overall optimization of the layering is a level of analysis that takes into account the form finding, takes into account the materials that you're going to use, takes into account the radiation protection analysis, and these give, and the pressurization, so the physics of the environment create the shape somehow. And I think in the simulation of the inflation, I think it's very well. So the entire structure is put into tension thanks to the pressurization, and then we apply all the loads, all the physics, and the radiation protection analysis, and then we create the shell. And this is true for the structure, the main structure. Regarding the interior design, what we did is a study on colors, material that can be extremely lightweight. So we use carbon fiber, we use textile, use also inflatable elements, for instance, for the mattress of their astronauts. So we are using elements that can be somehow innovative, but they can somehow be created in shape because of the shape that we designed. So it's a design exploration from the scale of the structure, and the interiors adapts to that structure. So it's created custom for that type of structure. It's not a standard element that we put in there. So
I guess the question is, how do you bring the stuff from Earth to the moon and build it there? Because these materials probably won't be producible on the moon, right?
Well, no. I mean, the interiors you can bring it directly from. You can bring it. The entire structure that is folded, and actually, I don't know how to activate here. Okay. So the structure is entirely folded within the textile, and then it inflates in its structure. And then you create the filling with the mycelium in the interlayers to create the radiation protection and the thermal insulation. And what you have inside, or you bring it with other cargo mission, or you can think of reinforcing the payload that the Argonaut lander could bring, because up to 2 tons, somehow you can bring just the membrane and the airlock by itself as an extra payload. And so, in fact, in our concept of operation, we thought of more mission in order to achieve the full completeness of this Argonaut lander. But it is thinking about the technology that is available now. Of course, if we reinforce the main structure, you can bring more mass. And you can also think of a way the entire structure could be deployed after. But happy to discuss with you later and these specifics. Actually, I invite you to use the VR that we bring.
But it's a very good question, and of course crucial to those designs. How possible is that actually, and how do we work on that and build the reality out of it? So that's why those designs are good, inspiring, and also asking the questions why. So, and how. Very good question. One last question. I saw one hand here over there. All right.
Hi. Well, thank you for the presentation. It was very good. And I guess my question is that by pushing the boundaries of architecture and thinking out of the box, there might be some findings that we can also apply to architecture here on Earth. So are there like interesting ideas that we don't use particularly now, but by doing this exercise, we can maybe think of deploying them on Earth?
Yes, I mean, the very first thing we are going to do is try to create the functional mock-ups of all these structures and create some analog structure that you can really simulate in relevant environment. So in different places here on Earth, this would be the very first thing, because we have to test the materials and the performance and the overall habitability. And so this would be the very first thing. The second thing is the change of, in terms of mindset and design, because since all these projects are computationally designed and in a multi-physics environment, meaning that you can simulate also the physics of the space, you can simulate certain things that just by drawing by hand you really can't, right? And so within that domain you bring back methodology on how you can create, if you can create an algorithm that solves this for space, you automatically can replicate the same exercise here on Earth. And here on Earth, we really need to be more sustainable, to use less material, to learn how to optimize our habitat, and do all these complex simulations. And last but not least, a very important part is the inclusion of robotics. So robotics in space is very pervasive, from 3D printing. That is one thing. It is mainly cited, but the thing is not the main aspect, because robotics will be very pervasive in different type of the habitability domain. And the robots will not just be anthropomorphic arm, but will be different kinds of robots with different shapes and configurations. And so another very important aspect that we bring from that lesson, we will really need to start improving our relationship with the robots, because human-robot interaction will become a thing even in our homes in the future. And then all the learning that we have when doing this exercise in space domain will need to be applied in our future homes here on Earth.
Yeah, designing for space is always also designing for Earth, I heard once, so it drops back automatically. I would say thank you very much, Dr. Valentina Sumini, for this awesome, inspiring close-up of this evening. Thank you very much again.